The use of deductive inference in science proved to be quite limited. Perhaps the most important example is that of Newton, who had to pay a cost to use deductive inference. He had to simplify the universe into an abstract problem, and based on that abstract problem, make assumptions and then deductions. But for most of science, the general laws are arrived by making numerous observations and then make generalizations. So let's see how deductive inference works. We're going to see three types of inductive inference. The first one is inductive analogy. In this argument, we have several premises and one conclusion. Arguments can have as many premises as we want, but only one solution, or only one conclusion. So, premises. x1 has property A, x2 has property A, x3 has property A, xn, let's say n equals 100,000, so x 100,000 has property A. I have only seen 100,000 instances of x. Conclusion, therefore, the next instance of x 100,001, has property A. So, we make a generalization from what we saw, a number of instances of x, to what will happen in the future. So the next encounter with that an instance of x, we predict that it will have property A. Now, you may notice that we are not guaranteed that this will happen, and so we don't have certainty like we did have when there was a valid argument in deductive logic. So let's see an example. Depressed patient 1 has anxiety, depressed patient 2 has anxiety, depressed patient 3 has anxiety, depressed patient n, let's say 100,000, has anxiety. I have only seen 100,000 depressed patients. Therefore, depressed patient 100,001 has anxiety. Okay, let's move to universal generalization. The premises are the same as in the previous case. x1 has property A, x2 has property A, and so forth. And then I have only seen n instances of x. Now the conclusion is different. Therefore, all x's have property A. So instead of just saying that the next time I will encounter an x, I will observe property A, we are saying that all instances of x have property A. Let's see an example. Depressed patient 1 has anxiety, depressed patient 2 has anxiety, all depressed patients I've observed have anxiety, therefore all depressed patients have anxiety. This is a generalization stronger than in the previous case. I'm not saying that just the only one, the next example will have anxiety. I'm saying that all instances of x or all depressed patients will have anxiety. So it's a stronger generalization. Let's move to the last of the types of inductive reasoning. Statistical generalization. Q% of all observed x's have property A. Conclusion, Q% of all x's have property A. So this is different than the previous one. I don't need to observe all the instances of something that have a property. It may be the case that only a percentage of them have that property, but I can still make an inference about the whole class of x's. and I can make an inference to what percentage of instances of X have the property. Let's see. This is by far the most popular use of induction in psychology. The generalization from a sample to a population, and we don't have the type of that all instances of something have the same property. Usually a percentage of instances have that property. Example: 60% of all observed depressed patients have anxiety. Therefore, 60% of all depressed patients have anxiety. David Hume, we saw it before, criticized the use of induction, or rather than the use of induction is the certainty that we can obtain from induction, because clearly there is no certainty that we are going to observe in the whole class what we observed in the sample that we collected. So in the case of 60% of the patients have anxiety, well, it may be the case that in the population of all depressed patients, that percentage is not correct. It's more than that or less than that. So allegedly, Hume criticized induction so much that he proposed to eliminate it, but that's not the case. What he said is that we need to be careful, that we probably have to get rid of the illusion of trying to come up with knowledge that is absolutely certain. So we need to use induction because that's the best we can do, but we need to be very careful. Things to take into account is the representativeness of the sample. So if we obtain a sample, we need to make sure that the sample is representative of the population. So if we obtain a sample that has quite different than the whole population, then the inference we are going to make from this sample to the population will be biased. Another thing to take into account is the size of the sample. If we obtain a sample of 1 or 2 cases and we want to make a generalization to a population, that generalization will not be a very good one. And related to the sample size is the error of the estimation. So when we make an inference or estimation of some parameter of a population, then we are going to have an error. It's not possible to make an errorless estimation, but we want to minimize that error, and we need to use tools to measure the amount of error that we have in that estimation, and that's what we do in statistics and apply it to psychology.